Good morning, everyone. My name is Javier, and today I will be presenting our research titled Selecting an Enhancement Process for Large Format Additive Manufacturing using the Analytical Network Process. This study explores new methods to enhance large format additive manufacturing throughout a multi-criteria evaluation approach, addressing critical challenges such as manufacturing efficiency, part quality, and sustainability. Large format additive manufacturing has emerged as a transformative technology in modern manufacturing, enabling the production of large and very complex parts with reduced material waste. Initially, it was developed for only rapid prototyping, but it has evolved into a robust technique capable of creating final components in industries such as aerospace, automotive, and renewable energy. Its unique layer-by-layer building process allows the fabrication of intricate geometries that will be challenging or maybe impossible to achieve using the traditional subtractive manufacturing techniques. The growing importance of this technique comes from its ability to enhance production flexibility, reducing the lead times, and minimizing the waste. Industries now rely on this technology to produce most of its components. However, despite its advantages, significant challenges remain. These include high production costs, inconsistent mechanical properties, and a limited range of compatible materials. Overcoming these limitations require an strategic approach that balances technological, economical, and environmental factors. New research efforts have focused on enhancing large format additive manufacturing capabilities, leading to an innovation such as non-planar printing throughout out-of-plane trajectories, allowing parts to be printed at 45-degree angles with improved structural properties. However, the development of the new materials and effective recycling process remains an essential strategy to be developed in the future. Addressing these areas will be critical to expanding its adoption across various industries. And in this presentation, we will highlight key evaluation criteria, discuss the proposed alternatives, and present the optimal solution identified through our analysis. We emphasize how these decisions can drive technological advancements and industry-wide implementations. We develop a comprehensive AMP model by consulting industry experts from the Institute of Design and Manufacturing here at the Universidad Politécnica of Valencia. And first of all, this involved defining the criteria, structuring comparison matrices, and applying pairwise comparison based on the expert output. We process this data using the SuperDecision software, and this software calculated the relative properties of each enhancement alternative. Our analysis focused on four main criteria, each broken down in relevant sub-criteria. First of all, we have the geometric criteria that is critical for application in industries such as aerospace, automotive, and renewable energy, where the precision and complexity matter the most. First, we have the complexity, and here in large format additive manufacturing, the strength lies in producing parts with intricate internal geometries, such as custom design aerospace brackets, and the enhancements that allow more complex shapes, reduce the need for post-processing, and expand the design possibilities of this technique. Then we have the tolerance margin, and maintaining tight dimensional tolerance ensures that the parts meet the strict specification, minimizing the costly rework and reducing the scrap waste that we have. Finally, we have the dimensions, the ability to fabricate larger components such as a wind turbine blade or automotive body panels expand the potential application of the production with large format additive manufacturing. Then we have the cost criteria. These are central to any manufacturing improvement strategy. And our evaluation of cost criteria focus on both direct and indirect expenses related to the technique. For the monetary cost, we have materials with really high performance, such as ABS reinforced with 20% carbon fiber that can offer superior mechanical properties, but they are very, very costly. Additionally, advanced processing equipment can significantly increase upfront investment and operational expenses. Then we have the time cost. While large format additive manufacturing can reduce the overall production time, maintaining operation temperatures up to 200 degrees Celsius requires a continuous energy input. This may lead to a higher energy bill, especially for the long production runs. Understanding and controlling this cost is essential for maintaining a competitive edge in large-scale production. Then we have the properties criteria that it can determine the performance, durability, and applicability of 3D printed parts. Our evaluation considering first the mechanical properties. The parts must withstand mechanical stress, especially in the demanding environments like aerospace and wind energy. And then we have the enhanced layer bonding and the material composition can made to improve the tensile strength and the impact resistance. Then we have the thermal properties. More components frequently endure long-term exposure to high temperatures in industrial ovens, so the material must retain the stability and resist the deformation over time. By focusing on these criteria, we aim to ensure that the enhanced large format additive manufacturing process will meet the industry specified the standards that are really high. Lastly, we have the operational criteria. That involves assessing how easily these enhancements can be integrated into the existing manufacturing process. And we have the time to adopt. The faster implementation minimizes the production downtime, and it may allow the manufacturers to remain competitive by reducing the time to market. Then we have the cost to adoption. Adoption costs include the equipment acquisition, the software licensing, and the requirements of the facility upgrades that it may happen. And finally, we have the expertise required. Advanced technologies like this one often require really specified training. So it may limit the pool of qualified operators and increase the training expenses. So this operational evaluation ensures that the proposed enhancement will not disrupt the production or incur in many excessive costs. Based on this evaluation, we have considered 4 enhancements alternatives. First of which is the laser heating. Applying localized heat using the laser improves the layer adhesion, but it requires a really high costly specified equipment. Then we have the non-pliable layers mentioned before. Is printing on curved surfaces enhances the strength and reduces the material use, but it may demand advanced path planning algorithms. Then we have the new materials, materials such as carbon fiber reformance or UTEM may be better mechanical and thermal properties than they used before, but it can also increase the production cost. Finally, we have the recycling process. By incorporating the recycled material, we can reduce the production cost and support the sustainability, but it's really hard to maintain consistent material properties, and it may remain a challenge in the future. So to ensure a well-rounded evaluation of the proposal large format additive manufacturing enhancement, we conducted a group decision questionnaire involving industry experts. Their input helped assess each alternative against the defined criteria used in the ANP, analytic network process. The results, as you can see in both graphs, reveal that the economical and operational factors, particularly the cost savings and the ease of adoption, were the top priorities. And the experts also highlighted recycling as the most important and promising option due to the potential for reducing the material expenses while supporting environmental sustainability. Also, we have the non-planar printing. It's a strong contender for its ability to improve part quality throughout enhanced design structure, and the alternative like laser heating and the use of new materials rank lower. It was due to the high investment cost and the complex implementation requirement. Then the AMP analysis provide a clear breakdown of the importance assigned to each evaluation criterion. Cost-related factors, including the monetary expenses and the mechanical properties, receive the highest weights, emphasizing the critical influence on the feasibility of the large format additive manufacturing improvement. This reflects in the industry focus on maintaining competitive production costs while ensuring that the printed parts meet the required mechanical standards. On the other hand, the criteria like expertise requires and adoption cost were way lower, indicating that as they will matter, they are not as decisive as material performance and production efficiency. This weight structure guided the prioritizing of alternatives, ensuring us a comprehensive evaluation process. Finally, for the AMP results, it confirms that the recycling is the most suitable enhancements for large format additive manufacturing. It has potential to reduce the production cost while promoting the sustainability. The second, as before, is the non-planar printing that shows promise to show a promised future due to its ability to improve the mechanical performance, but it faces a implementation challenge required advanced hardware and software. Finally, to talk a little bit more about the recycling process that is currently used in the large format additive manufacturing, is only based in the use of milling waste, also called as scrap material, and this is the only material that is used for recycling. Neither the molds or the final parts are being used, and this scrap material is processed by a shredding mill. This shredding mill reduces the diameter of the grain so it can be easily processed, and this grain is taken to a twin screw extruder where the material is melted and the filament is formed. Then this filament is cut into the right dimensions to create the new recycled pellets that are going to be then fed into the 3D printer to make the new parts. As you can see, this process is still very expensive and too many specified machines are needed. Also, we can see that very little material is reused. So this is why, such as an important alternative as recycling, we propose a new methodology to enhance this technique. In this new methodology, we have two key aspects that can be highlighted. The first of which is the molds that will be used as feedstock, in addition to the scrap material that was used in the classical methodology. On the other hand, we have the elimination of the twin screw extruder. So it's proposed to use only the feedstock with the repelletizing directly from the grinder mill. So this methodology offers several advantages. The most important ones are the increase of the useful life of the molds, allowing them to be reused and not making them immediate waste after the first use. And in addition, the cost of both material and machinery can be reduced since it would only be necessary to purchase a ready mill to produce the recycled material. The main disadvantage of this methodology is the lack of knowledge of the behavior of the material, but therefore there should be work to characterize this new material. In conclusion, our research demonstrates that the recycling is the most viable enhancement strategy for large format additive manufacturing. It provides sustainability and is a cost-effective solution while supporting the broader goals of environmental conservation and resource optimization. The main key takeaways that we can have is that recycling offers significantly cost savings and environmental benefits, addressing technical challenges such as non-planar printing could unlock new design possibilities, and future research should be focused on long-term recycling effects. Hybrid manufacturing approaches and enhanced quality control methods are the future to be studied, and these findings open pathways for innovation while reinforcing the importance of adopting sustainability technologies in modern manufacturing. We acknowledge the support of several funding projects, and these contributors were instrumental in conducting our research. And this is all for today. I hope it was a good time for you. And if you have any questions, I will be very happy to answer them.